All right, so just some announcements. So we're doing review today for lab. I mean, we're pretty much done with lab. We're not going to be doing any more experiments. We'll come in one of the days um, after the exam to do checkout and do more exam review. That's pretty much what we're going to be doing for lab days is just review. So I'll send out more information about all of that as it comes. But just as far as this week, I did post the next unit's lectures. So those are up there. And that will kind of conclude what we're going to be doing for this next exam. So it's kind of a weird mix because I'm throwing in conjugation and dienes with spectroscopy. So it's like they're two kind of completely unrelated things. But so the last part of the exam content is on today's lectures, and it's just one day of lectures. So there's a problem set up there, and I've also included a blank copy of my notes. If you want to use them, that's fine. If not, then you don't have to. But that's all up there for Unit 12. After that, there will be one more unit to go through, and I'll have those up there sometime after next week's exam. And that will be it as far as the content. Obviously, that won't show up until the final exam, but there will be elements of that last unit on the final. Um, and I think that's about it as far as announcements. So next Monday, week from today, we'll have our fourth exam. Again, in room, whatever room that is, 516. Um, and like last time, you can have a note card. You'll be able to have a note card for the final as well. So I think that's it. Any questions? Okay. Like I said, I'm going to just go through the problem set from the NMR chapter, and we'll just kind of go until people want to quit or, don't feel free like you have to stay the whole time. So, um, all right. So one of the important skills for both carbon NMR and proton NMR is being able to predict the number of signals that either one will show. The concept for both is exactly the same. You need to be able to identify unique regions or unique chemical environments. Okay. And in the beginning, it's helpful to kind of draw in everything. So if you're looking at proton NMR, I'm just going to draw in all the hydrogens. So I'll just put like CH3, CH3, and then put the hydrogens in here. And let's just kind of start outside of the benzene ring and just pick one as a starting point. I'll call those A. Um, Now, if you remember from the videos, I kind of give you, it's not a rule, it's a recommendation, so to speak, that hydrogens on the same sp3 carbon are usually equivalent. That's not 100% of the time. But one type of hydrogen that's always equivalent are CH3s. Okay. So all three of those that I labeled as A are equivalent to each other. Now I'm going to come down here and look at these. I'm just going to put this, question mark. Is that second set of CH3s equivalent to the first? One way you can judge that is what are they connected to? So this one's connected to that quaternary carbon, and these here are connected to the same, or connected to the carbon that's also there. So those are equivalent. And then I would say the same thing for those, because they're all in that same chemical environment. If you build a model kit of this, one easy way to see it is if you spin it around, each CH3 gets to see the same environment. Okay, so that's another way that you can use like a three-dimensional model to help you with that. So all nine of those are equivalent. Um, Now, can I say the same thing for the other nine? So if I label this as B, are the B CH3s the same or different than the A's? Yeah, because if I cut this molecule in half, everything on the top half looks exactly like everything on the bottom half. And so these are actually more of the A hydrogens. So all 12 of those are equivalent to each other. And imagine if I were to take this and flip it end over end, I get the same thing. So that's another way that you can like look at, well, how do I mean, they're so far away. How are those even equivalent? It's because I can take the molecule and flip it on itself and I have the exact same thing. So whenever you have that symmetry, you got to be kind of careful what things are related by symmetry. Now, if all those are A, I'll just start here with this hydrogen and call that B. Do you see any that look exactly like B? Well, you could say the ones across from it or the one across from it also the same. What about the other two hydrogens on benzene? Are those the same or are they different? Those are the same. Because again, they're related by symmetry. So this compound, even though it's got a ton of hydrogens on it, would only have two signals on its proton NMR because of all that symmetry. Now, if I change this up and I put a different group down at the bottom, then that kind of, blows the whole thing out of the water. But because of that, the related to that symmetry, the top half looks exactly like the other half, then those hydrogens are going to be equivalent. Yes, same thing. Yeah, signals peaks. Yeah. So we're actually, well, let me modify that. If you're looking at multiplicity or splitting, that's a little different because that's when you're talking about singlet, doublet, triplet stuff. Yeah. Actually, you know what? Let's kind of let me highlight something here, going on that route. The B hydrogens there, would those show up? What kind of signal would they show up as, like in terms of singlet, doublet, triplet, whatever? Singlet, because they're equivalent to each other. They can't split each other. Okay, even though they are adjacent, they're not on the same carbon. Because they're both B hydrogens, they're both the same, they don't split each other. If somehow one was B and just for the sake of argument, one was C, then they would split each other and they'd both be doublets. But because they're equivalent, then they would just show up as singlets. Same thing with this. All nine of those hydrogens would have the same signal. It just would be a singlet because there's nothing adjacent. All right, so let's look at this one. And again, I'm just going to draw in all the hydrogens. And let's start off. Oh, I forgot a hydrogen. One right there. Let's start off on the end here and just call those three hydrogens A. Now, CH3s are always, the hydrogens are always equivalent to each other. Can I say the other CH3 on the other end is exactly the same because they're both CH3s? No, because one's closer to the chlorine, the other one's farther away. So right away, I'll call those B. Now this one here with the chlorine is off, there's nothing else like it. It's on the same carbon as the chlorine, so that's unique. And here's where you have to be very careful. If you have a stereocenter present, CH2s tend not to be equivalent to each other, even though they're on the same carbon. Because if there's already a stereocenter, then what happens is you have to imagine replacing one of those hydrogens. So I'm going to replace this one with some random group. And then I'll replace the other one with some random group. And if I were to ask you, if we look at those two results there, what's the relationship between those two compounds in terms of stereochemistry? They're diastereomers. So what that means about these original hydrogens here is that they are diastereotopic. Meaning they kind of have the potential to become diastereomers if you were to rip one off and put something else there. And the thing about diastereotopic hydrogens is they are not equivalent to each other, even though they are on the same carbon. And if you think about why that is, the hydrogen with the solid wedge is always cis to the chlorine, right? And the hydrogen with the dashed wedge is always cis to the other hydrogen with the dashed wedge. So they kind of are experiencing different chemical environments. And so we would call this one D and this one E. So there would be 5 signals for this one. And then it gets a little complicated with splitting. I never really would ask you, well, what's the splitting of D or E? Because D splits E, and it's also being split by B and C. It's going to look like a big mess. So I would never really ask you to interpret that. I didn't go into complex splitting. So you wouldn't have to worry about like, well, is that supposed to be a quartet or triplet? It's going to look really weird. All right, let's look at C. And again, I'm going to draw in the hydrogens here. Once you get really good at this, you don't have to necessarily draw them all in. It's just helpful in the beginning. And we'll start off at those 3 hydrogens on the end. They're equivalent to each other. They're on a CH3. Do you see any others that look exactly like that? Yeah, imagine if I cut this in half, that molecule is related by symmetry. So everything on the left is equivalent to everything on the right. Now, CH2s are where I need to be kind of careful, okay? Because sometimes they are equivalent, sometimes they're not. Again, you kind of go through the exercise. We'll replace one of the hydrogens with a group and then replace the other one and see what the relationship is. If I do that with these CH2s, I would only create enantiomers. And so those 2 hydrogens, this set as well as this set, are both enantiotopic, meaning they're equivalent to each other. We just kind of like ignore that stereochemistry stuff. So both of these are equivalent to each other. I'll call them both B. And because this compound's related by symmetry, the other one is the same. So 2 signals. All right, let's look at D. And again, I'm going to draw in all the hydrogens here. All right, I'll start with this guy, call that A. There's no other ones like it. No, nothing else with the chlorine around, so that's unique from the other 2. What can I say about the 2 that are involved in the double bond? Are they the same or are they different? So again, let's look at this in terms of symmetry. Okay, imagine that hydrogen coming out at you, the chlorine going away from you. I'm splitting it right down the middle. So I got the same thing on the left and the same thing on the right. Those are going to be equivalent. So this one would only have 2 signals. Even though they're not on the same carbon, they're related by symmetry, and so they have the same signal. All right, let's draw in all the hydrogens here for E. And then I'm going to draw the 2 in here. All right. I'll start here, call this one A. Any others that look exactly like that? Yeah, the CH3 on the other side. Because those hydrogens, and I go through this in the video, those CH3s are homotopic, meaning I don't create any sort of stereocenter. They're going to be equivalent to each other. Now, how about these here? The H's that are also with the chlorine. Oh, yes, I'm sorry. There we go. And so with these, even though they're going in not the same direction, they still have the same stuff around them. So those two will be the same. It's the CH2 in the middle that we got to be careful with. Okay, CH2s are always like the weird ones that we got to look out for. Okay. If I imagine replacing one hydrogen or the other, I get a pair of diastereomers. And so because these are diastereotopic, this one's different from this one. So 4 signals. And then finally on the last one, again, let's draw in all the hydrogens. And we'll start down here with this. So are there any other hydrogens that look like A? Yeah, these up here. So all 6 of those are equivalent to each other. And then that one's just a single hydrogen, unique to itself. Now I know I drew the CH2 with some stereochemistry there, but are those the same or are they different? Do I already have an existing chiral center? There's no other chiral center around. So I don't say at worst, those hydrogens can only be enantiotopic. Because if I replace one or the other with some random group, I get enantiomers. And enantiotopic hydrogens are always equivalent. So these two are exactly the same. Now the remaining 3 hydrogens, they're on a double bond. So are they automatically equivalent to each other? No, I mean, this one's kind of closer to all the stuff. And the 2 on the end are farther from each other, or they're like the farthest away from everything. But when you are dealing with pi bonds, you have to be careful because this hydrogen is stuck looking at that one. And this hydrogen is stuck looking at that group. Because I cannot rotate around a double bond, the top hydrogen, the green one, will never get to see the bottom half of the molecule, never get to be in that environment. And so this one is different than this one. So here's another instance where hydrogens on the same carbon are not necessarily equivalent to each other. So you'll see this in 2 ways. Either they're diastereotopic, like if it's an sp3 CH2, or they're part of a double bond. That doesn't always mean if I have a CH2 and a double bond, they're automatically not equivalent. I just have to see what the other groups are. Because if I had the same group on the top and the bottom, then they become equivalent. And I go through another specific example like this in the lecture, um, highlighting the difference between those 2 hydrogens. So we get, let's see here, 1, 2, 3, 4, 5, 6 signals for that one. All right. Any questions on this page? Yeah. So this, oh, because if I were to replace one group or the other, I would just get enantiomers. And so that makes these hydrogens enantiotopic. And enantiotopic hydrogens are always equivalent. Okay. Let's look at this one. So we're just doing some predictions here. Okay, so first thing we're going to do is let's predict how many signals we should see. Okay, so let's just start with that. Those are our A hydrogens. It's a CH3. Because this is related by symmetry, that means everything on the left is going to be the same as everything on the right. And then I have my B hydrogens there. Now let's talk about splitting for our A hydrogens. When it comes to splitting, just pick one or the other. You don't have to look at them totally, just look at one or the other. Um, so how many hydrogens are adjacent to A? Two. So in terms of splitting, what's that going to turn out to? A triplet. Remember the n+1 rule. So A should show up as a triplet. And B, how many hydrogens are adjacent to B? Three. All right, so B is going to show up as a quartet. Now let's kind of do a little bit of chemical shift predicting. I'll start off very general. Which one should have the higher chemical shift, A or B? B is closer to the more electronegative stuff. Okay, and A is farther away. And whereabouts would a hydrogen right next to a single bonded oxygen show up? So this is why it's kind of good to have those kind of generalities in your mind. Right next to an oxygen like this is probably going to be somewhere between 3 and 4. Maybe a little on the higher end, like 3.5 or so, because there's some other stuff around. And the A ones are farthest away from everything. Okay, just kind of a regular old sp3 hybridized carbon. So maybe around 1. And so let's put those things on here. Let's just say, this is 1, 2, 3, 4. I know it's not to scale, but it is what it is. And so I'm going to put my quartet between 3 and 4. I know it's not, well, try to make it at least a little symmetrical there. And I'm going to put my triplet somewhere around 1. Now, before I move on, I want to highlight kind of a common template that you should always keep in the back of your mind when interpreting NMR. Whenever you see a quartet triplet like this, that usually means an ethyl group. Because this will be our quartet, that will be our triplet. So that's one of those little tricks to remember. There's probably some very rare exceptions out there for what other some other stuff they could mean, but generally, for all the problems you're going to see, for all intents and purposes, a quartet triplet is a good way to just throw in an ethyl group into your structure. And if I'm going to predict integration, what is integration? Not the number of signals, but yeah, the number of hydrogens. The number of hydrogens that that signal represents. So it could be as simple as saying, well, this represents 2 hydrogens and this represents 3. Or if you wanted to get like, how many does it actually represent? You could say, well, this represents 4 and this represents 6. I would accept either answer, whatever ratio you wanted to use, as long as the ratio is correct, of like a 2 to 3. Okay, let's look at B. And I'm going to start here, call those two hydrogens A. Are the two hydrogens of A and the two right next to it, they're both CH2s, are they equivalent because they're CH2s? No, we're using the chlorine kind of as like a locator. And those two hydrogens, the B hydrogens, are farther away from the chlorine. And then those three are different. So three signals. Let's kind of estimate what A would show up as. What would be the splitting for A? Yeah, it'd be a triplet, okay? Because it's next to two hydrogens. So show up as a triplet. What would B show up as? Yeah, it's got two on one side, three on the other. After quartet, after three adjacent hydrogens, we just start calling things multiplets. Technically, A and C are not equivalent to each other, so it's going to look a little weird. But if you just want to say, well, I got two and three, that should be like a sextet signal. If you wanted to draw it the way, that's fine. And what would C show up as? A triplet. All right, now let's do some chemical shift predicting. What should have the highest chemical shift? A, it's closest to the chlorine. Okay. Um, and you can kind of estimate, maybe we'll just say somewhere around 4. It's highly electronegative, so it's going to shift it pretty far downfield. B is a little bit farther away, but it will have a slightly higher chemical shift than C. So I'm going to put it a little bit above 1. I'll just say 1.2. I'm not trying to be exact. I'm just trying to say it's somewhere above 1 because it's kind of close to the chlorine. And then C, I'll put it somewhere around 1, maybe a little below it. All right, so here's 1, 2, 3, 4, 5. And I'm going to put my triplet at around 4. And then that multiplet just above 1. So 1, 2, 3, 4, 5, 6. And then the triplet right below 1. And if I'm going to do integration, how many hydrogens does the A represent? 2. And the multiplet B represents 2, and the triplet represents 3. Again, if you wanted to do like 4 to 4 to, well, you wouldn't really do that for this one, but because that's the B hydrogens, there's 2 of them. All right, and then let's look at how many, yeah, the last one here. So let's just predict how many signals we should see. I'll start up here at those CH3s. Any just like it? Yeah, the other CH3 here, because they're both attached to this carbon here. Now I do have another hydrogen right there. Don't want to miss that. It's kind of easy to miss those sometimes. So just, like I said, sometimes it's helpful to draw everything in. And I will draw in the benzene hydrogens here. And I'll call this one C. Are there any that are exactly like C? Yeah, the one above it is, but because this isn't related by symmetry in terms of this way, the other two are not the same. There is symmetry related this way, though. And so both of these are D. And then I'm going to draw in that aldehyde hydrogen and make that E. So 5 signals. Okay, and so let's start predicting what they should look like. The A hydrogens, what kind of splitting would the A hydrogens show up as? Doublet. They're only adjacent to one hydrogen. What would the B hydrogen show up as? Yeah, multiplet because it's there's six of them there, or six A hydrogens adjacent. What would the C hydrogen show up as? Doublet. And the D hydrogens, those would be a doublet as well. And then how about the E hydrogen? Anything adjacent to it? No, one carbon over is a carbon without any hydrogen. So E would show up as a singlet. Now let's do some chemical shift predicting. Which one would have the highest chemical shift? E. Remember, aldehyde hydrogens, carboxylic acid hydrogens have the absolute highest chemical shift of all protons. So aldehyde hydrogens, I don't know, we could say somewhere around 9 to 10. Carboxylic acid hydrogens are usually 10 and above. So let's just say 9. Which ones would be the next highest? Yeah, you're right, D. Yeah, the D hydrogens. The benzene ones would be kind of close together, but D is kind of more closer to that electronegative stuff, the oxygen, than the C hydrogens. So I'm just going to kind of estimate and say D would probably be, we don't want it to be higher, so I'm just going to say like 7.5. And I'm going to say the C's around 7. Again, my benzene hydrogens are around like 6 to 8. So anywhere in the middle of those is going to be completely fine. This is just an estimate. Now, which one would come next? Which one would have the next highest chemical shift after our aromatic ones? We did C and D. Yeah. So between A and B, which one would be next? B. B is benzylic. Okay. And benzylic hydrogens start to show up between 2 and 3. So I'm going to put it somewhere between there. And then A's are kind of regular. So there is a benzene ring somewhat close. So I'll just say like 1. Maybe it is a little bit above 1, but I'm not going to split hairs if questions like this show up on an exam. As long as you're not putting like the A hydrogens down at like 10, okay, they belong around the 1 area. All right, so let's start putting them on here. And so I'm going to put my singlet for E around 9 or 10. There it is. And then I'm going to have a doublet at around 7.5. And around 7, there'll be another doublet. And then around 2 to 3, I'm going to put my multiplet. There's my multiplet. I don't know if that's the right number, but that's multiplet. And then I'm gonna put the doublet at around 1. So if I do integration now, again, I'm going to go left to right. The aldehyde hydrogen, there's only one of them, so 1H. Each of my benzene protons, I have 2 of them. How many protons are there for the multiplet? Just one. There's only one B hydrogen. And how many A hydrogens? 6. So the integration for that would be 6. All right. Any questions on these? All right, now let's get to actual interpretation here. So I will kind of let you know, like on your exam, you're going to have some interpretation problems where you're given like a single spectra like this. And then you'll have some kind of similar to at the end of this problem set, as well as the extra problems I gave you on your notes. We're going to be given multiple spectra, and you have to come up with the structure. Okay. So the problem set has quite a few of those types as well. Um, so the first thing that you always want to do is get a formula. If the problem gives it to you, well, that's something you don't have to worry about. So in this case, look at your formula. Don't look at the spectra yet. The formula tells you what you should be showing in your structure: carbon, hydrogen, and oxygen in this case. Okay, I can't tell you how many times in exams over this content, students will have that formula given to them, and then they'll start putting halogens in there or sulfur atoms or whatever, because I don't know, they looked in the IR fingerprint region when they weren't supposed to, and they're like, oh, I read somewhere that that's a carbon sulfur bond. Don't do that. Okay. Only include in your final answer the atoms that are there. Now, the next thing you do with the formula is find IHD, the index of hydrogen deficiency. This is something that I go into in the notes or in the videos for this unit. It basically will tell you kind of a summary of how many pi bonds or rings that you have. So the way you calculate IHD is you need to kind of in your mind, if that compound were fully saturated, if it had 5 carbons, how many hydrogens should it have if it were fully saturated? 12. You use 2n plus 2. Because remember the formula for a saturated alkane is that? So if it had no pi bonds or no rings, it should have 12 hydrogens. But it doesn't. It only has 10. So I'm going to subtract those 10 hydrogens from it. Now, if an oxygen is present, I don't do anything to this calculation. Okay. If there is a halogen, then you add 1 to this term. If there is a nitrogen, you take away 1 from that term. Those are the only ones, the most common ones that you'll see. But I don't do anything with oxygen. And then divide the whole thing by 2. That comes out to a value of 1. What 1 value means is you have either a pi bond or a ring. Now, the next thing I would recommend to do is look at your IR. There's no IR given in this problem. So the only other information we're given is a proton and a MAR. And right away, we can try to narrow down that 1 value of IHD, because if I have a carbon-carbon double bond, where do protons show up if they're on a carbon-carbon double bond? So vinylic hydrogens are around 5 to 6. I don't have any signals there, so I probably don't have a carbon-carbon double bond. What's the other type of pi bond I could have? Carbon-oxygen double bonds. And one of the giveaways that kind of leads me to, yeah, I probably have a carbon-oxygen double bond, is those alpha hydrogens next to them show up on proton NMR around 2 to 3. And you'll notice that I got 2 of those signals that show up between 2 and 3. So what I'm going to do is start there. I'm going to draw a carbonyl, and then I'm going to assume there's 2 things to it. Why do I assume there's 2 carbons next to it? Because I have 2 alpha protons giving a signal there between 2 and 3. Now, how do I know this isn't an aldehyde? I'm assuming it's a ketone, but I kind of skipped over this. How do I know it's not an aldehyde? Yeah, there should be a aldehyde signal around there. I don't have one. Okay. So let's focus on those two signals between 2 and 3 right now. Notice I have a triplet and a singlet. Singlet's like a big red flag for me. Because if it's a singlet, how many hydrogens is it adjacent to? None. So how do I have a carbon here that fulfills the octet rule and not adjacent to any hydrogens? It's a CH3. That would give me a singlet, right? And it's happy, it fulfills the octet rule. Now let's go to the other side. So that signal right around 2.5-ish or so is a triplet. It kind of zooms in there. That's what this big one right there is. How many hydrogens does something need to be adjacent to make a triplet? Two. So I know whatever this proton is right here is next to two hydrogens. And I'm just gonna like fill in the octet for this guy here. Just give it another hydrogen. So I took care of the two things around the carbonyl there. Now let's go to this signal. It's like a big multiplet. Was that 1, 2, 3, 4, 5, 6? How does something have 6 hydrogens adjacent to it? Or, well, no, sorry, let me back up. How do you get like a sextet? Like how many adjacent hydrogens should it have? 5. Okay. Well, if I'm assuming that CH2 is represented by that multiplet, I have 2 on one side, I got to have 3 on the other. So I want to put 3 on the other side. I've kind of finished my problem here. I mean, it fits the formula. And these 3 hydrogens over here represent that triplet. That CH3 on the end is adjacent to 2 hydrogens. So one of the easiest things to do with a proton and a MAR is pick a starting point. Notice I started at the carbonyl and I built everything around it. Rather than just try and be like, well, I see that signal at 1, it's a triplet, like start with the central point and then kind of build outwards from it. All right, any questions on this one? All right, let's look at another one. Again, proton NMR only. Oh, I'm sorry. No, no. We haven't even talked about the naming of ketones. So, yeah. All right, so first thing, again, approaching any sort of interpretation problem is focus only on the formula. So carbon, hydrogen, and 1 bromine. I'm going to find the IHD. So if this has 8 carbons, how many hydrogens should it have if it were fully saturated? 18, right? 2n plus 2. But it doesn't have 18. It's only got 9. And it's got a bromine in it, a halogen. Okay. We treat halogen when it comes to IHD as if it were a hydrogen. It occupies the same space with the same number of bonds. So in this case, or a halogen is a hydrogen, so to speak. So that's why I'm adding a value of 1 there, because that 1 comes from the presence of a halogen. So 18 minus 10 divided by 2 is a value of 4. Now, I could probably spend another half hour trying to write out all the possible combinations of what 4 could mean. But most of the time, not every time, but most of the time, a value of 4 or more means you have a benzene ring present. Because if you look at benzene, it's got three pi bonds and it's a ring. So that's a value of 4. That's always a great starting point when you have like a high IHD value like that. Okay, so notice just from the formula, like I already got 6 of my carbons placed. All right, so my benzene hydrogens are going to be right there between 7 and 8. I'm not going to try to interpret that. That looks like a big mess right now. I'm going to kind of, I know they're there. I know I have benzene. I'm just going to kind of keep on going here. The only other two signals I see are triplets. Okay, so one of them is adjacent to two hydrogens, and the other one is adjacent to two hydrogens. Well, how do I get something like that? I have this kind of template. And on one side, there's no adjacent hydrogens, and on the other side, there's no adjacent hydrogens. So notice I'm kind of looking at this like a puzzle piece. How do I put that puzzle piece of two CH2s onto benzene? Well, just put it there. Notice on the left side, I got benzene. There's no adjacent hydrogens to this guy right here. Kind of out of everything though. I'm out of carbons, I'm out of hydrogens. And I got a carbon right there that's not happy. What's left? Bromine. So if you're kind of at this place where it's like, wait, I put everything up there and I got something that doesn't have an octet rule, we know we're supposed to have another atom in there. So that's where my bromine's going to go. So all 5 of these benzene hydrogens are being represented by that big clump of signals. Benzene hydrogens get really tricky because you can go through them and say, well, I should see like, a couple triplets and a doublet. These guys are equivalent to each other. These are equivalent, and that's unique. But because they all tend to have very similar chemical shifts, okay, it's like if you take your hands and then mix your fingers together, you can't really tell which is which. That's what's happening with these signals, is their chemical shifts are so close together, they're overlapping, and it looks like a big mess there. All right, and so this is going to be our answer. Now, I do again want to highlight with spectroscopy, every single piece of data should line up. Okay. It shouldn't be like, well, I got this structure, but I mean, the splitting's kind of off. My integration doesn't work out just like the spectra says it should. It's close enough. I mean, close enough only works in horseshoes and hand grenades. So, doesn't work in spectroscopy. If it doesn't fit every single piece of data, then either maybe you did something wrong in lab, got some wrong data, or your answer is wrong. Now, I will say, and this is on video, so you can bring it back to my attention. Um, I do give partial credit on problems like this, depending on how close you are to the right answer. Okay. So if you're like, well, I got benzene there and I put the bromine somewhere else, that's somewhat close to full credit. If you're like, oh, I'm just going to draw something that's got a bunch of carbons, and then I'm going to put like, some pi bonds like this and put a bromine there, that's not even close to anything. You're not addressing that fact that it's aromatic or anything. So very little credit. But so there is a range of um, available points. Okay, so it's not like it's an all right or all wrong thing. Okay, so on this one, I do want to kind of make some clarifications. The source I got this from was like really, I don't know, it's like computer generated. I don't think it's an actual spectra. So it's missing some things. This signal here should be a quartet, and it might not look like it, but that is a doublet. All right, so let me back up a little bit and let's look at the formula. C6H12, so I should only have carbon and hydrogens in my answer. I'm going to find the IHD. It should have 14 hydrogens if it were fully saturated. It's only got 12, so that's a value of 1. So I have either one pi bond or one ring. How do I figure out which is which? If I look at my proton NMR, is there anything there that would suggest I have a pi bond? Can't have carbon oxygen because there's no oxygen there. Is there anything to suggest a carbon-carbon double bond? Remember, vinylic hydrogens show up where? Somewhere between 5 and 6-ish. So that's kind of how I verify. If those weren't there, then it's quite possible I have a ring instead. So that's where I'm going to use kind of like as my starting point. I'm going to build everything around it. Actually, I'm going to go down below. Now, this also gives me some big clues. Because they each represent one hydrogen, I know it has to be internal. Okay, that's the only way I can have one hydrogen and still fulfill the octet rule. So I'm going to put stuff around that double bond. That also gives you like a little separate side note. If one of them represented two hydrogens, what does that tell you about the location of the double bond? It's terminal. That's the only way you could have two hydrogens on a double bond is if it's terminal. Okay. Now what I'm going to do is kind of go down the line a little bit. I have a couple of these that are somewhat higher than the others. Those are around the area where you'd expect allylic hydrogens to show up. Remember how I did this with the carbonyls? Or the very first problem we did? Okay, I started with the carbonyl and then I looked at those alpha protons. They're both kind of in similar regions. So it's the same thing here. Those are kind of showing up around the that vinylic region. I'm sorry, not vinylic, allylic region. So I have one allylic proton on one side and another on the other side. I'm going to zoom out so you can look at the integration. This one represents two hydrogens, that one represents three. So fill that in. Here's my three hydrogen one, and there's my two hydrogen one. Can I add anything else to the left? No, CH3s are where the chain ends. So I'm done going to the left. Now all I can do is go to the right. How many more carbons do I need to put up here? My formula says C6. I've already drawn 4. So draw the other 2. And what are the only things I can put on those carbons? Hydrogens. So make them fulfill the octet rule. And let's just check and see if this makes sense. What would these hydrogens show up as in terms of splitting? Well, I got 2 on one side, right? And I got 3 on the other. So that's a big multiplet. Notice what I got right here? A multiplet representing 2 hydrogens. And then how about these three on the end here? What would those show up as in terms of splitting? How many are they adjacent to? Two. So it'd show up as a triplet. And what do I got there? The farthest away from everything, the lowest chemical shift is a three hydrogen triplet. So again, notice I'm not just trying to randomly like, where do I start? Start at, like a landmark, just like I did on the first problem. I started with the carbonyl and built around it. This problem, I started with benzene and built around it. This one, I started with the double bond and I started building around it. And as I said, only things that your whole answer should match every single piece of data. Right? Yes. Yes. So like that's why this one, let me get a different highlighter color here. These three here, because they're adjacent to one, would show up as a doublet. Oh, on the double bond? Yeah, it's kind of, yeah, because they look like singlets, right? But you have to remember that since this hydrogen is not equivalent to those, it's not going to look very clean. Okay. And vinylic hydrogens on double bonds are very rarely nice looking. Usually on a problem, something like this, I would highlight what the splitting would be. So that it's like, well, is that supposed to be a triplet? Maybe if I squint, it could be a quartet. Like I don't want that sort of ambiguity. Okay, so let's do another one. So first thing, look at your formula. Don't even look at the spectra. Because I don't know about you, when I see something, like this and just like it freaks me out first because I don't have any information, look at the formula and start there. Okay, so it should have, we'll start with your IHD. How many hydrogens should it have if it were fully saturated? 16 plus 2, 18, right? But it only has 8. I don't change the math for oxygen. Oxygen doesn't do anything to this calculation. And that comes out to a value of 5. Now, right away, the first thing that's going to appear in my mind is I'm going to say that it's quite possible I have benzene because that has a value of 4. And I have one other unsaturation, probably a pi bond. Is a ring possible? Not with that few carbons to have two rings like that. It's going to look really weird and strained. And yeah, a ring is highly, highly, highly unlikely, or I should say a second ring. So I'm going to say the fifth thing is going to come from a pi bond. I have a lot of oxygens here, so maybe a carbon oxygen double bond. We'll just figure out if that's the case. Now, the other thing that we can try to do is I have two oxygens there. Okay. There's kind of a few possibilities for this, but if I have a carbonyl, in my mind, I'm going to not limit myself to say, oh, that should be a ketone. What about functional groups that have multiple oxygens, like an ester? Those have two oxygens in it, or a carboxylic acid. Like what's that rule? Occam's razor, whatever. The easiest solution is usually the right one. So don't try to come up with extravagant things like How many different ways can I put two oxygens in this compound? A lot. Okay. So make it easy on yourself. And then if those don't make sense, then you can go to the harder things. Now let's go to our spectra here. Is there anything to suggest what this functional group could be? If I know I have benzene, that's my group there between um, 7 and 8. Do I have anything to suggest what my pi bond could be? What? Right. Could be an aldehyde. I have a couple oxygens, so it's, well, yeah, let's go with your aldehyde theory. Let's go with that. No, let's go with it. Okay. Yeah, because aldehydes are going to show up there. And then I already said like my two hydrogens here, or I should say all four of those represent benzene. Let me give you a little insight here about how you can arrange stuff on benzene. Notice I have two separate signals. Each of them have two hydrogens. Okay. That generally means I have one group on one side of benzene. I'm going to put X as a generic group. And I'm going to put directly opposite a second group, X and Y, because those two hydrogens will be the same. And those two hydrogens will be the same. And that's how I'll get two sets of benzene hydrogens, each of them with an integration of 2. There's no other way. Practice this at home. Arrange X and Y. We're assuming X and Y are different in various positions next to each other, one carbon over and opposite each other. There's no other way to get two hydrogens and two hydrogens except to have them opposite each other like that. Now, let's start here and put all our pieces together that we know so far. We know we have benzene, and we're going to use the recommendation of an aldehyde. So let's put an aldehyde there. I can't go any further because the aldehyde's the end. So let's work on what the other group could be. What other atoms do I have left? How many carbons do I need to put on there? I have to put 8 total, and I got 7 up there right now, right? I got one more. What other atom? An oxygen. Okay. So let's see if this gives us any insight. That signal there, right around 3.77, of how I can range that oxygen and carbon. So again, this is why it's helpful to kind of have some numbers committed to memory. Hydrogens next to like single bonded oxygens show up between 3 and 4. And it's a singlet, which means what? What does a singlet mean? Yeah, right. There's no hydrogens adjacent to it. And so these 3 hydrogens have nothing adjacent to it. And it's next to an ether oxygen. Those hydrogens show up at around 3 to 4. So yeah, your aldehyde hydrogen recommendation was, I mean, you could think of it, it could be a carboxylic acid, but I like that better because let's look at this and let me kind of explain why it can't be a carboxylic acid. If I put both my oxygens there, then the only thing I could put here is a CH3. Now, that fits the splitting, but the signal is between 2 and 3 for a benzylic hydrogen. So was that enough? Yeah, that's a big enough difference to say that that cannot be the right group that should go there. Another possibility that is not completely correct is an ester. That fits this. But what's wrong with that? What's wrong with this? How many signals should I see for benzene? One, two, three. And so it doesn't fit the aromatic data. And this again goes back to my something I said before. Every single piece of data has to work, has to line up and be correct, or it's not a fully correct answer. All right. Any questions on that one? Keep going. You don't feel like if you're like, I think I got this. If you don't want to stick around, I'm not forcing you to stay. So I'm just going to kind of go through the rest of the problems here, and we'll just see how far we can get. All right. So first thing is let's start with our formula. Now we can see what atoms should be there. And let's calculate the IHD. So it should have 10 hydrogens. It's got only 9, but it also has a chlorine. Okay, so this value of 1 is coming from the halogen. So that's an IHD of 0. Like, is that possible? Absolutely. It just means it's fully saturated now. No pi bonds, no rings. Now the IR spectra shows only alkane peaks. Okay. That's huge because that kind of tells us what we should be looking at for that oxygen. If we don't have any pi bonds, what are the possibilities for that oxygen? That oxygen can either be an alcohol or an ether. The IR says, hey, there's no alcohol peak. And the carbon oxygen single bond shows up in the fingerprint region, like around 1,000 or so reciprocal centimeters. So that's like why we wouldn't really look there. So the fact that we don't have an OH tells us we probably have an ether. Notice we got all of that just by looking at the formula and a little bit of IR information. Now let's look at our proton data. Like that doesn't look like a picture. How am I supposed to interpret this? We're just going to use the same data or same process. We just don't have, a picture in front of us. Okay. Notice I have 4 signals, 4 carbons. That's a good indication you probably do not have a symmetrical compound. Every single hydrogen is unique. All right, so where do I start with this? Well, if I'm going on the assumption I have an ether, I'm going to just start my puzzle right here. And I'll put 1 hydrogen on each for right now. I probably will put more on after that. But where are those hydrogens that I drew going to show up? If they're right next to a single bonded oxygen, where should they be? It should be around 3 to 4, right? Okay. And notice I got a couple signals here, like a 3H and a 2H right in that area. Well, I guess I can probably try to include all of them, but I have signals between there, okay? So I'm just going to put a 3H there on that side. And I'm going to put a 2H right there. Now, I don't know if you caught on to this or if you've seen this kind of in some of the videos. This is a little bit, well, a lot of trial and error because we might draw a structure and find that it doesn't fit all of the data. And that's okay. We just kind of go back and reevaluate. I'm going to move this over real quick just to give myself some room. Now, if you look at what I've done here, I've only got two more carbons to put up here. So let's just put them on here. There's only one way, one order they could possibly go. If you look at this last signal, I have a 3H doublet. The only way I can have a 3H like that far away, is if it's a methyl group. And so by process of elimination, I have this last 1H as a multiplet. If you look at it, this hydrogen right here, I'll highlight it real quick. It's got 2 on one side, 3 on the other. That's going to be a pretty messy multiplet. I'm missing something though. I have one more like valency to fill in, and I'm out of hydrogens. What's the only other atom I'm supposed to show here? Chlorine. That's where I'm going to put it. Okay, and so that's the only answer that is going to fit every single piece of data. Now, why did I put the chlorine there? And not here? Like, what would be the kind of biggest indicator for why that second answer is not the right answer? I'll give you a little bit of a hint. I'm going to draw on one hydrogen there to really emphasize it. That hydrogen I just drew in there is right next to an oxygen and a chlorine, very highly electronegative. So if this normally starts between 3 and 4, and then I put a chlorine there, that's going to shift it even farther downfield, probably to like 5, 5.5. And then I don't have a signal there that high in this in the data. So that's why I can't have that possibility. All right, any questions? All right, let's keep on going. So now we're getting into like multiple spectra here. All right, regardless of whatever you're given, start with the formula. Okay, so it should have, we'll calculate the IHD first, should have 20 hydrogens. It only has 10, and oxygen does not affect the calculation at all. So that comes out to a value of 5. Now, what is a good assumption at this point as far as what could be part of my structure? Benzene. I have a large number of carbons, at least 6. Okay, I know I'm going to have benzene. So because benzene is going to take up 4 of those, and then probably one more pi bond. So either carbon oxygen or carbon carbon. If I just take a quick look at my proton NMR, is there anything there that would kind of suggest I'd have one or the other? Yeah. So you got this here. We know it's a peak because they put an integration number there. And that is also how a lot of times how carboxylic acid hydrogens show up is this like very, very small, kind of broad little signal. And it's a super high chemical shift. All right, so now let's just start with those two things in mind. So I have benzene and I have a carboxylic acid. I'm just going to start off by putting the acid here just to put it somewhere so I can see it. I might not keep it there. I'm just going to put it there, see if it fits the puzzle later. If you look at the integration for benzene, the benzene hydrogens right here, that is a big clue about how you should arrange everything else around benzene. Because notice it says there should be 5 hydrogens. If I put the carboxylic acid on one side and some other group on the other side, how many benzene hydrogens do I have with that? 4. So the fact that I have 5 benzene hydrogens means it's mono-substituted. It's a big fancy word for one group. Now, obviously, I got to move that acid now because I have some like sp3 or hydrogen on sp3 carbons there. And that kind of tells me I should have 2 sp3 carbons on my carbon NMR. So I'm going to get rid of this for right now. And again, I'm going to use the integration to help me because the integration says both of those signals are two hydrogens, right? So let's draw two like this, CH2, CH2. And now I'll put my acid back. Are these two hydrogens the same or different? These two are not equivalent. So that's why I see two different signals, both on the proton NMR and for the carbon NMR. Two different signals. Now, if I really want to like check my answer, let's practice looking at the carbon NMR. What kind of signals right here that at that high, at around the 180 mark? Yeah, that's our carbonyl. Okay, but we know it's an acid, so we'll just go ahead and put an acid there. Yeah. But the only thing that shows up that high from 160 and above are carbons of carbonyls. Notice you got 4 signals there between the carbon-carbon double bond region. So that fits this template here with the monosubstituted benzene because we have 1, 2, 3, 4 signals. And then as we said earlier, those are 2 different sp3 hybridized carbons. Any questions on that one? Okay, let's keep on going. All right, so first things first, look at the formula, calculate IHD. So this should have 26 hydrogens. It only has 18, and I don't do anything for oxygen. So that comes out to a value of 4. All right, so again, best assumption to make for that is that we have benzene. Yes. Well, so if something has 12 carbons, if it were fully saturated, it should have 2n plus 2 hydrogens. So that's where the first number comes from. The second number comes from how many does it actually have. Now, the only other information we're given about the possibility of what that oxygen could be is that there's a broad peak at around 3,500 centimeters. What kind of functional group has a very broad signal in that region? Alcohol. So right away, it's kind of giving you an idea, okay, there's probably an alcohol in your structure. Okay, so let's look at our data. And first things first, though, start our template. We know we're pretty confident there's benzene. What kind of hydrogens are represented by these two signals? What kind of hydrogens show up between 6 and 8? The benzene hydrogens, right? And if I have two of them, each of them representing two hydrogens, how does that tell me I should arrange groups around benzene? I'm going to put them opposite each other. Okay, and I don't know what those are yet. I don't want to kind of randomly guess. Let's kind of take a look at the rest of our data here before we start, wasting time on guesses that might not work. So let's address that signal at 3.25. Okay, it's a 1H and it says kind of broad peak. I don't know if you've seen this in your textbook or in various problems. That's usually, if I know I have an alcohol, they kind of show up not like massively broad, but they're not like thin signals. Sometimes you'll be given information where it says that this signal exchanges with D2O or it disappears when you add D2O, because what's happening is the hydrogen of OH doesn't do this with other hydrogens, but the hydrogen of OH, if you add D2O, deuterium oxide, the hydrogen exchanges with deuterium and suddenly disappears from the spectra. So you might see that information as well. That's kind of like a red flag that signal represents the OH hydrogen. All right, then if I go down, I see again two hydrogens and two hydrogens. Maybe those are CH2s. But what I want to I'll come back to those. I want to get to the last one there. How the heck do I get 9 hydrogens? Yeah, a terbutyl group. It's impossible to have 9 hydrogens on one carbon. So let's spread them out amongst 3 carbons. This is a very common template that you should know. If you see a 9H signal, that's probably a terbutyl group. If you see like a 6H signal, that's very commonly an isopropyl group. So let's start making some assumptions here. Let's say, and we'll verify this, okay? Again, trial and error. Let's say our terbutyl group is one of the groups on benzene. All right, we're going to put it down and then we'll evaluate. If it doesn't work, we'll fix it. That means I'm going to have these other CH2s on the other side. And for that very last carbon to be happy, that's where I'm going to put my OH. If I look at the data, that kind of makes sense because this hydrogen right here is right next to a singly bonded oxygen. So I'd expect it to show up between 3 and 4. And this is a benzylic hydrogen. Which normally they start at around 2 to 3. And it kind of makes sense that it's pretty high because it's close to an oxygen on one side, really close to benzene on the other side. So that's why it's on the higher end of that 2 to 3 range. And if I look at the blue and the pink hydrogens there, what kind of signal would the blue hydrogen show up as in terms of splitting? Triplet. So it's adjacent to 2 hydrogens. Now the pink one, I want to address that for a second because you'll notice in the data, it says that it is a triplet, but yet it's got 3 hydrogens adjacent to it. Again, OH hydrogens are very weird because they're constantly doing this exchanging. A lot of times they don't split. And so when it comes to splitting, generally ignore OH hydrogens for splitting. And that goes both ways. We're not going to look at that OH hydrogen and say, oh, it should be a triplet because it doesn't split. And we're not going to look at that pink CH2 and count the OH hydrogen in our N+1 rule. Right? Any questions on this one?
OH would make it a triplet. Is that what you're saying, or it's a thought?
Well, technically, if the OH hydrogen were splitting that CH2, you'd have 2 on one side, 1 on the other. It'd show up as a quartet. But the OH hydrogens don't split stuff. So you're only looking on the one side.
Yeah.
All right, let's look at the next one. So we got a lot of data here. This is a great kind of example of a problem you might see on your exam where you have a whole bunch of spectra. And a lot of times I might ask you individual questions about each spectra. Like I might say for this one, make a list of the functional groups that are there. You know, circle the absorption, label with the appropriate group. You get points for that. Okay. I might tell you to go down to the proton NMR and, you know, tell me some things about that. What, you know, what does the splitting tell you about adjacent hydrogens and, you know, so on and so forth. Okay. Or like carbon NMR. Like what are the hybridizations of each of the carbons, that sort of thing. So that way you might not be able to get to the correct structure, but I can give you points along the way for correctly interpreting each individual spectrum. All right, so first thing, calculate the IHD. So just for the sake of time, I'm going to go through the calculation, but that comes out to a value of 1. So pi bond or a ring. Do I have anything, now that we have an IR there, do I have anything in the IR that might help me figure out that value of 1? What? Yeah. So you got this. What could that be? That carbon-carbon double bond. What really clinches it is there's an sp2 carbon hydrogen signal there. Both of those pieces together would imply that I probably have an alkene. This is just regular old sp3 stuff. I have an oxygen here. If my pi bond is tied up with carbons, that means I can't have a carbonyl. What are my only possibilities that I can use that oxygen for? Ether, okay, or an alcohol. Can I eliminate one of those possibilities? Yeah. How do I know I don't have an alcohol? Yeah, no broad peak there. So just by looking at the formula and the IR, I know what my functional groups are. I got a double bond and I got an ether. So let's go to our NMR here. And a lot of times I like to kind of jump back and forth just to verify data. But if I think I have a carbon-carbon double bond, let's draw that first and build on it. Here is my vinylic hydrogen data between 5 and 6. What does this tell me if I have an integration of 2 for vinylic hydrogens? It's a terminal alkene. That's great because now I could just start adding stuff down the line. Now let's look at kind of the rest of our proton NMR data here. Notice I have 2 chemical shifts that are kind of in a very similar region, and then one that's off like the farthest away from everything. If I think I have an ether, what kind of hydrogens do you think those are? Well, yeah, they got to be CH2s. They're probably next to the ether, the oxygen, though. And before I start drawing anything else, look at the relationship between these things here. I have a quartet and a triplet. Remember that little tip I gave you, like almost at the beginning of this lesson? Quartet triplet generally means ethyl group. So how am I going to use that to put the rest of the carbons up here? I'm going to put a CH2 next and put it next to an oxygen. That's this guy right here. Then I'm going to put my ethyl group because this CH2 will be that there, and that CH3 will be that triplet. Now, one thing I want to address real quick, I'm going to go back to the signals between 5 and 6. They look really weird, right? Okay. That is because all 3 of these vinylic hydrogens are not equivalent. And so what is happening here is A is splitting B and A is splitting C. It's going to look really weird. B is splitting A and B is splitting C. It's going to look really weird. So that's why this 2 hydrogen thing looks really weird. Doesn't look like a quartet or a triplet or anything like that. So think of again, you can't rotate a double bond, right? So A only gets to look at C. It's stuck there looking at C. But B only gets to look at that rest of that ether stuff down below. So These two things are stuck looking at each other, and these two things are stuck looking at each other. They don't get to rotate around. Does that make sense? Yes, because yeah, because the double bond, yes. Yeah. All right. Now what I'm going to do is kind of like let's just go through the carbon NMR process. Notice those two signals there represent my carbon-carbon double bonds after, between 100 and 160. The rest are going to be sp3 hybridized carbons. And those two with the highest chemical shift, or the ones between 60 and 80, have to be next to the oxygen. And then the last one is just the farthest away from everything. It's at the end of the chain. All right. Any questions on this? All right, couple more. Now, this one, in my opinion, is kind of the more frustrating, more difficult examples, and you'll kind of see why in a little bit. Let's calculate the IHD. So it should have 18 hydrogens, but it only has 14. So it comes out to a value of 2. Now, what students, a lot of times what they do is they look at that and say, oh, 8 carbons, I got to have benzene. That's not always true. Okay, there's a lot of organic molecules that have a lot of carbons in them that don't have benzene. And the IHD kind of confirms that. And I have a lot of oxygens. Okay. What you should kind of keep in the back of your mind is if you have a lot of oxygens, don't always say, oh, they all got to be involved in alcohols or they got to all be the same thing. Okay. When you have multiple oxygens in your mind, think of it as a possibility that you have some functional groups that have more than one oxygen in them. So it's possible to have a carboxylic acid or two carboxylic acids or an ester or one of each. Like start thinking outside that box of just one single functional group. Now, if I look at the IR, do I have alcohols? Do I have a carboxylic acid? No, there's no massive OH groups here. Now notice that I don't have any carbon-carbon double bonds, right? There's no sp3, I'm sorry, sp2 carbon hydrogens. It's just sp3 carbon hydrogen. What could that signal at around 1700 be? Yeah, carbonyl. So it is quite possible that I have an ester. Why am I thinking that's a possibility? I'm just trying to get to the easiest solution possible. The easiest solution in my head right now is if I have 4 oxygens, then maybe my compound has 2 esters in it. That's all I'm making a very big assumption that might not come true, but we'll see. Now, here's where the confusing thing comes in. If I look at my proton and carbon NMR, it's very unremarkable. I have 3 signals here, 3 types of hydrogens. And in my carbon NMR, if I look at the proton decoupled spectra, I have 1, 2, 3, 4 signals. 1, 2, 3, 4. This one here is the solvent. Just ignore that. What does that tell you? If I have fewer number of signals than carbons, what does that tell you about the structure of the compound? This is something I do mention in the videos. Yeah, symmetry. Okay. Now let's look at our proton NMR. One of the things that jumps out at me is I have a quartet and a triplet. What does that generally mean? Ethyl group, quartet, and a triplet. And notice how what would be my quartet has a pretty high chemical shift between, or after 4. So where would I put this in the compound? Well, if I assume I have an ester, what would make most sense to put the ethyl group on the carbonyl side or the single bond oxygen side to get that high of a chemical shift? Like, would I want to put my ethyl group here or here to have a high chemical shift? I want it next to the oxygen. And then I have some other stuff here. Now, I'm going to do something that is going to be incorrect right now. Okay. But I'm kind of setting up where you should start to think because we already said there should be a lot of symmetry, right? So what if I just said this? Okay, that's a symmetrical compound. What's wrong with that? Yeah, I'd only see 2 signals. Okay. And I don't have the near as enough atoms is what the formula tells me. Okay. But this is not necessarily a bad thing because I'm going to start with this template of having 2 esters make a symmetrical compound. Is there anything from this carbon NMR that might help me decide what those last 2 carbons should be? I'm missing 2 carbons. Where should I put them? Or in fact, what are they even going to be? What do negative signals represent in DEPT 135? They represent CH2s. Now, I already have one CH2 represented here. The one's right next to these oxygens. Where is the only possible place I could put that CH2? Exactly. Well, in between what carbons? Yes. I'm going to toss them in right there. They can't go in my ethyl groups because the ethyl groups have to stay ethyl groups. So the only places I can put them are in between the carbonyls. Now I put 2 there because I only have 2 more carbons left. Why are they exactly the same? Why do they give the same signal in the proton NMR? I'm looking at the green ones that I highlighted there. So why are the hydrogens there in my answer? Those 4 green hydrogens, why are they the same signal? Yeah, that's where our symmetry is. If I cut this compound in half, everything on the left is exactly the same as everything on the right. Bless you. All right. Any questions on this? Uh, because sp2 is right above 3000. I know it's kind of, yeah. Usually like there will be a small signal and there is a gap between the 3000 and the sp2. All right, last one. So again, let's look at our formula. And the IHD for this is going to be 1. So go through the math. I'm not going to do it right now. We've done it 100 times already. Now, one thing to keep in mind is that in this formula, there are 3 oxygens. Okay, so start thinking about functional groups that have multiple oxygens in them, like carboxylic acids or esters, those sorts of things. Now, next step is look at your IR. Okay, so what's that big signal around 3400? Yeah, definitely an OH. What about at 1700? What's that big signal? Carbonyl. Should I assume that that's a carboxylic acid? No, in fact, you don't want to do that because remember, carboxylic acid OHs will go like into the sp3 region. That's the big difference between alcohol OH and a carboxylic acid OH. So that takes care of my 2 oxygens, or 2 of them. I need 1 more. Again, I'm going to make an assumption that one of my OHs comes from the alcohol, another oxygen comes from a carbonyl, and maybe the third one comes from an ester. I mean, it's possible it could be an ether somewhere else, but with only 4 carbons, like that doesn't leave me a lot of possibilities to have 3 different functional groups. 2, maybe. It's easy to it's a lot more plausible for something with 4 carbons to have an OH and an ester. But to have an OH, an ester, and an ether, that's a little far-fetched. Okay, so let's look at our proton NMR. Now, right off the bat, what I want to highlight, this is a little kind of tip that's given. That signal there before 4, where it says it vanishes in D2O, that's going to verify you have an alcohol. Because alcohol hydrogens exchange with deuterium in deuterated water, they will disappear when you add deuterated water. So that just confirms we have an OH. Now let's kind of look at and see if we can find any of our little tricks here. This signal at, I don't know, what is that, 4.2 or so? Above 4.2 is a quartet. This looks like a singlet. And this looks like a triplet. Now, as a side note on an exam, I would have given you those if it looks kind of like vague. What's a template or what's a trick that you can do with the quartet and triplet? Ethyl group. And what do you think that CH2 of the ethyl group is attached to have this high of a chemical shift? Yeah, next to an oxygen. And if I'm going to assume I have an ester, let's, we know we got to have a carbonyl somewhere. How many carbons do I have left? 1 more. So let's put it there. I got to put an alcohol somewhere. And there's my last remaining hydrogens. These two hydrogens are represented by that singlet. Why are they a singlet? The alcohol hydrogen does not split. Okay, when it comes to like splitting, you ignore counting it in your n+1 rule. So technically, those green hydrogens don't have any other adjacent hydrogens because we don't count that OH one. All right, and then the carbon NMR just kind of verifies what our guess is. So here's our carbonyl. Notice in the DEPT 135, there's two CH2s. I really would review that DEPT NMR. I talk about it at the end of the NMR videos because it really is a pretty important tactic because this shows us that we should have two CH2s. We wouldn't be able to get that with just the normal carbon NMR. We don't know whether those should be CHs, CH2s, or CH3s. And essentially, this DEPT 135 tells us that both of those are CH2s. Okay, which is what we drew in our structure here.
However, one facing upward, is that your CH3?
So if it's upward in 135, it could be a CH or a CH3. We know from our structure that it should be a CH3. That's kind of like the downside. There is another version like DPT 45 that would distinguish between CHs and CH3s. All right. Any questions on this last one? Yeah. Yes, and you can see that through splitting as well. Yeah. Yeah. So there's multiple ways that you can verify what that should be. Yeah.
The chemical, they're like pretty close, not just kind of.
Because they're both next to single bonded oxygens. Okay. This one here is also next to a carbonyl. So maybe that's the slightly higher chemical shift one. All right, any other questions? Okay, so that takes care of this problem set. I'll post this up on Canvas, kind of act as the key, and you can kind of go back and grade your self-grade your homework. And then I will put this video up as well on Canvas, so that you can refer back to it. Wednesday's review, I'm gonna go through some of the problems that are in the end of the notes from this unit, from Unit 11, and maybe even throw in some stuff from the Unit 12, because Unit 12 will show up on the exam as well. So you'll want to make sure you listen to that. Try to listen to it before the review session, but definitely over the Thanksgiving break as well. So I'll send out the Zoom link for Wednesday because it'll be online, and there's no reason to, show up if you don't want to. Well, I'm not going to be here, but if you got to be on campus for other stuff, that's fine. Yes, I will record that Zoom meeting. Yeah. Okay.